So last lecture was really satisfying because there we finally understood how we can do control design using the state and then at the same time figure out what the state is, and everything works thanks to this fantastic principle known as the separation principle. So what it tells us is that we can completely decouple control and observer design. And here I have a rather important little parenthesis that says, in theory. Now, there is a great American thinker that has figured out that this in theory is actually kind of important. This is Yogi Berra, a baseball player, who presumably said, in theory, theory and practice are the same. In practice, they are not. Now, this is rather profound, and it has some implications on the fact that just because the theory tells us something, we need to be aware of certain things at least. So the first thing we need to be aware of is the controller is really only useful once the estimated state is close to the actual state. Meaning that the controller doesn't really do anything useful until the observer has converged. So what we want to do is we want to make sure that the observer converges quickly. What that means is that we want the observer to be faster, which in turn means that these eigenvalues that we're picking should be larger for the observer than the controller. Now, one thing we saw with large eigenvalues, though, is that we get large gains. So in the control side, this is kind of bad because that means that we have large actuation signals, which means that we can saturate the actuators. In the controller side, the observer side, that's no big deal because the observer is entirely done in software. There is nothing that's going to saturate. So we can actually make our observer eigenvalues large without having to run into issues like saturation. So practically, what we need to do is pick the eigenvalues, typically in such a way that the controller eigenvalues are all, first of all, they all need to have negative real part, of course. And then what we want to do is we want to make the observer eigenvalues bigger, because that means that the observer is faster than what the controller is. So here is a completely made-up eigenvalue selection, but the important thing here is that the slowest observer eigenvalue, which really dictates how quickly the observer converges, is significantly faster than the slowest controller eigenvalue. So that's something that we typically want when we're building our joint observer control design structures. Okay, having said that, let's actually use this to control a humanoid robot. And this is the Aldebaran now that we're going to be working on. And in fact, what we can control on this thing are joint angles, meaning how the different angles are moving. And luckily for us, we actually have detailed models of these joint angles. In fact, for a given joint, the angular acceleration is 1 over j times ki minus b theta dot. And these things, well, they are physical things. So j is the moment of inertia. I is our input, right? So I is actually equal to u here in this case. This is our input to the system. This is the current we're applying at the motor. Well, k is a torque constant and translates roughly currents into accelerations. And then there is always a friction coefficient, a viscous friction coefficient in these motors. Now, luckily for us, when you buy a robot like this, someone has already figured out these physical parameters, and there are user manuals that describe what these parameters are. Now, we need to put this on state space form. And the first thing we're going to do, as always, is say, well, x1 is theta, and x2 is theta dot. Right? We're also going to say that what we can measure on this thing is the angle itself. So y is going to be equal to theta. Well, with this choice, we get a linear time invariant system that looks like this. X dot is 0, 1x, 0 minus b over jx, and then we have this b matrix, which is 0k over j times u. And y is 1, 0x, since we're pulling out the orientation. Now, one nice thing about this system is that it is completely controllable and completely observable. So what we have indeed learned in this class should be applicable. Okay, so let's do that. The last thing we want to do, though, is we actually don't want to hold or stabilize the now into all the angles being 0. We want to be able to move it around. So what we want to do is we actually would like to track a reference angle. We would like the angle of the joints to be something. So I'm going to define a new variable E, stands for error. It's not the estimation error, it's another error, which is the current angle minus the desired angle. And then I'm, as the second variable, tossing in the angular velocity. And I would like to drive E to 0, because if I have E equals 0, then I have theta equal to theta desired, meaning I'm holding it at the angle I would like. And I have theta dot equal to 0, which means I'm actually holding it there. I'm not moving through it only. Okay, so this is what we would like to do. Okay, then we need to write down the dynamics for our new variable E. Well, E dot, well, it's simply AX plus BU, because E dot is really, well, it's theta dot minus theta desired dot theta double dot, right? But this thing is 0 because the desired heading is constant. So all we're left with is theta dot theta double dot, which is the same as x dot, right? This is the same as x dot. So what we do is we plug in the equation for x dot, and we get this. Now, we don't want to express this in terms of x. We want to express it in terms of E. And what we get if we plug in E is we get this expression instead. Now, luckily for us, A times this vector is actually equal to 0. And I encourage you to compute this so that you trust me. But having done that, what we get is that E dot is equal to AE plus BU, meaning we have the same system dynamics as before, but now defined on this error, where the error is the current orientation or angle of the joint minus the desired angle of the joint. So this is the dynamics we're caring about. Well, we have to do the same thing to the output. The output is Cx. Well, again, we replace x with E plus this vector. So this is CE plus C times this vector. And remember that C was actually 1, 0. So if I take 1, 0 times that, out comes theta desired. So my output is C times E plus theta desired. Now, this doesn't scare us one bit. We just plug it into our standard controller and observer design methodology. So U is minus K, not E, because we don't know E, but E hat, which is our estimate of E. And E hat dot, well, it has the standard predictor part, and it has the corrector part. And the corrector part is the current output minus what the output would have been. And the only difference here is I have to keep track of this little extra theta desired. But it's no big deal. It acts exactly in the same way. So this is now my control structure. And instead of me talking about it, why don't we move on to see an actual humanoid robot executing this control strategy? So now that we have designed an observer-based state feedback controller for controlling the joint angles of this humanoid robot, the Aldebaran Now, we're ready to do it for real. And I'm here with Amy Laviers, who is a graduate student at Georgia Tech. And what she has done is made the Now move its arms and its head and even its upper body in such a way that it is executing a friendly wave towards probably you who are watching this right now. And what's happening is we're running the same controller on all the different joints with different desired angles to get the effect out. So, Amy, why don't we take the Now for a little spinner and see what it can do? So what's going on here is that we're sequentially running multiple desired angles, and that's how we're getting this effect. In fact, why don't we watch this again, because I think this is quite charming, to be honest. So here we go. Observer-based state feedback control in action. Well, thank you very much, Amy, and thank you. So personally, I think this is remarkably satisfying to do all this math and write down all these matrices, and at the end of the day, we get a robot that waves its arms around. It's hard to beat that as far as I'm concerned. Now, what I would like to do during these very last moments of module number 4 is to say something about how would we do if we want to go beyond pole placement. And the first thing I should point out is that this structure that we have developed is very, very general, where we have state feedback, U is minus Kx hat, and observer design, copy of the dynamics, and this observer gain L. Now, the thing that I would like to point out is that K and L, they do not need to come from pole placement per se. There are other ways in which you can design them. And I just want to say a few words about those. Let's start with K. Well, one very common way in which people design Ks is not to pick eigenvalues, but instead use something called linear quadratic optimal control, or LQ optimal control. And the idea there is to define a cost on your system that says something about how the system behaves. And what you have here is a penalty on x, meaning how much x is deviating from the origin. And here we have another penalty on u that says how much control effort is involved. And the design parameters now are not the eigenvalues, but these weight matrices. And what you want is you want q to be positive semi-definite and r to be positive definite. This doesn't matter too much. I just want to tell you that it's possible to pick other things than eigenvalues. And it turns out that the solution to the LQ optimal control problem is given by K on this form, which is R inverse B transpose times P, where P solves this mouthful of an equation. This is known as the algebraic Riccati equation. But the whole point I want to make here is really not that you should memorize this algebraic Riccati equation. I'm just saying that there are other ways of doing the design if you don't feel like picking eigenvalues. So a perfectly good thing to spend a Saturday evening doing is looking up LQ optimal control and seeing, okay, what are the other ways or other knobs out there. Similarly, L can be picked in other ways. And for instance, there's something known as the Kalman filter that allows us to pick L in a slightly different way. The Kalman filter is defined typically in different ways. One can talk, for instance, about the steady state Kalman filter. And what this is dealing with is if I have an input noise here, this is some kind of disturbance, and I have some measurement disturbance. These are Gaussian noise or white noise with zero mean. If I have this, then the thing that minimizes this, which is the steady state expected variance, so how far in variance you're going to be, the mean is obviously going to go to 0, but the variance may not be 0. So the thing that minimizes this is an L that looks something like this, which is a little bit of a mouthful. Again, it involves a P matrix that satisfies a different looking algebraic Riccati equation. But the point here is not these particular choices of K and L. What I want you to be aware of is that there are different ways of doing this control design. And again, if you spend Saturday night looking at LQ, you spend Sunday night looking at the Kalman filter just as a way of seeing an alternative to pole placement. But to wrap up, we feel really, really good about ourselves because we can do control design now. Now, unfortunately, the real world is more complex than a simple LTI system. So what we're going to do in the next module is, based on what we've done in this module, deal with more complex scenarios. And what we're going to produce are something called hybrid systems, where the pieces are LTI systems, but where we have to switch, for instance, between having the robot go towards a goal and not slamming into obstacles, and do that in a systematic and careful manner.